Wilbert, and we're going to listen and talk about categorified tangle invariants and the Schrödinger fiber.
Yeah, thank you, and thank you very much for the invitation to speak. So, I want to start very basic by recalling the definition of the Temple-Ellipse category. So TLQ, so this is going to be the CQ linear monoidal category, which has objects, just basically non-negative integers. And in this context, I'm just going to view such a non-negative integer as a collection of, say, n points on a horizontal line. Okay? So then, morphisms in this category are supposed to be the following. So a homomorphism, say, from n to m points in this category. So, well, how do we define it? Well, first of all, we can consider compact one-dimensional cobordisms from n to m, say, embedded in R cross the interval. So, and I think of the n points as sitting inside R cross, well, the subset here consisting only of 0, and the m points here sitting inside R cross 1, okay? And so I'm considering these things up to isotopy. And what I really want to do is linearize this, as I said. So we want to have a CQ linear category. So what I'm going to do is I'm going to take the span of all of these diagrams and then mod out by this relation that I can remove circles at the cost of multiplying by Q plus Q inverse. So an example of this, so let me just draw one example quickly. So something like this. This would be, for example, so this would be an element in HOM TLQ from, I guess, 6 to 4, okay? And this is not a basis element, so this one has a basis element. So the basis of this, of a HOM space, is basically given by all these crossingless matchings where you don't have the circle. So this wouldn't be a basis element because you can still remove circles by this relation. Okay, so this is something that we all know very well. So why are we interested in something like this? So let me also recall this really quickly. So let D be some tangle diagram. So I'm going to try to draw an example here to keep in mind. So let's just look at this thing. So that's a diagram for a tangle, and then we also orient everything, say like this. And well, what we are generally interested in here in this conference is we would like to assign to such a tangle diagram some kind of invariant. So let me in this context just call this FD. So, and well, FD being an invariant in this context, of course, means I want this FD to be, well, constant under certain Reidemeister moves. If I do a Reidemeister move on this diagram, I don't want the FD to change. And also if I perform just a planar isotopy here, of course, I want to get the same FD. Okay, so what I want to discuss now quickly is the Jones polynomial, which we all know very well, using this Temple-Ellipse category. So what we can do is, once we have such a tangle diagram D, we can look at a crossing, so something like this. And then there are two ways to resolve this. So basically I can do something called a one resolution, let's say. So then I look at a crossing in here and I replace it by, I think I want this for the one resolution. And for the zero resolution, I just replace it with a cap pair. And once I do this, of course, this picture will become an element in the Temple-Ellipse category. So what I can just do is I can take S. So S is now what we call a complete resolution. So I'm going to replace all these crossings by, well, some complete resolution where I either do a 0 or a 1 resolution for each crossing. And then I take the sum over all of these possible resolutions. And if I want to have the correct formula, I have to correct these things by some factor of Q inverse. And this mod S here, so this is just supposed to be the number of 1 resolutions of this resolution S that I choose, okay? And this one I'm going to call FD unor. And the reason for this is because I haven't really used the orientation yet. Okay, so this is not my final answer for this, but what we can already see is that this is going to be an element in one of these home spaces of the Temple-Lieb category. Okay, so now in order to finish this, so let me put the theorem down here. So this is something that you can check now quite easily. So if you take some diagram D of, say, an oriented NM tangle, so the N and the M, so they correspond to the number of endpoints and also, well, the points at the bottom and at the top. So, yes, so if I have an oriented NM tangle here, so then I can do the following. So my FD, so this is now actually going to be the following. So I simply take the FD unor, which doesn't depend on the orientation, and then there's some factor here in front which depends on the orientation, and I have to explain one thing for this. So let's distinguish two kinds of crossings. So I can have a crossing like this. So this one I'm going to call a positive crossing, or alternatively I could have something like this, which I'm going to call a negative crossing, and then this factor is simply given by n plus. So this is just the number of positive crossing in this diagram that you start with, and then you multiply this by q times n plus minus n minus. I guess that's the right formula, and you still end up with something in here. Okay, and you can check now that this is an invariant. Okay, so this is something that everybody knows very well here. So now I want to do something on this side of the board, which I guess a lot of you don't know that well. So in order to illustrate this, let me, so since we are in Vienna, so you should think of these boards as two parts of Vienna, and then I'm going to have the, so how do you say it in English? Donau? What? Danube, okay. So this is Vienna. So here you have the Danube, and these things don't really have anything to do with each other yet, okay? Unless you are an expert and already know all of this stuff. So I'm going to do something completely unrelated. So yeah, so what I'm going to do now is I'm going to consider GLM, let's say. So the Lie algebra GLM. And what I'm going to be interested in is a certain affine subvariety in here, but yeah, so which is given by all nilpotent elements in the usual sense of linear algebra. Okay, so you have M by M matrices here, and you look at the nilpotent ones. And then you can act on this thing simply by conjugation. And so what you get is, well, this action kind of gives a disjoint unit, or, well, you have certain orbits here, and if you take a disjoint union, well, you get the whole n. Okay, so I'm interested in the nilpotent orbits. Okay, so an orbit under this action is called a nilpotent orbit. And the first question now is, can I classify them? And so this is something that we all know from linear algebra. So let's take x, okay, some nilpotent element here, and I look at the corresponding orbit. So what I can do with this is I can bring it to Jordan normal form, okay? So then I have a couple of Jordan blocks, and each of the Jordan blocks, they kind of look like this, okay? And I can arrange them in such a way that the size sort of descends along the diagonal. So what this actually gives me is a partition, okay? And so what I actually get is a one-to-one corresponds between these nilpotent orbits and partitions. And how do I get it? Well, as I said, so you take an orbit, pick some element inside the orbit, bring it into Jordan normal form, and this is, I'm going to call the Jordan type of X. Okay, so the partition that you get from reading of the different sizes of the Jordan blocks. Okay, so this is going to be called the Jordan type. So now, where else have we seen partitions before? I mean, they appear at many different places, but one very prominent place would be if you consider finite dimensional irreducible representations of the symmetric group. So SM in this case. And I should say that I'm working over the complex numbers, okay, throughout the whole talk. So then we know that there's also one-to-one correspondence between partitions of M and these finite dimensional irreducible representations, and I can take a partition and just send it to S lambda, the corresponding irreducible Specht module. Okay? So this is what many undergraduates know, but the question now is, so once I have this, is this sort of just a combinatorial coincidence, or is there some deeper meaning behind this correspondence between orbits and these irreducible representations? So this is now an obvious question. And in this case, the answer is yes. So basically, can I go directly from here to here without ever having heard of partitions? So that's basically the question. Okay? So, and sort of the whole point of Springer's theory is basically that you can actually do this. And I'm going to explain quickly how you can do this. So how do I get from here to here? So I'm going to take an orbit corresponding to X, some nilpotent element, and then I associate to this some algebraic variety. And yeah, well, this is pretty explicitly given, so I can write it down for you, so that's a nice thing. It's actually quite a combinatorial object, at least for me. So you can look at flags. Yeah, so flags inside C to the M, so something like this. So how do I get the nilpotent into this whole game? Well, now I'm going to just say, well, if I take the nilpotent and I act on the ith space, then I want to end up one space below in this chain, okay? So basically, your nilpotent hops you along such a flag. So if you consider all of these flags which satisfy this condition, this is called this Springer fiber over X. So that's a projective algebraic variety, and it's actually quite interesting from a geometric point of view, because it turns out that this is not smooth. So, and it decomposes into many irreducible components. But the good news is that they all have the same dimension, at least. So it's not complete chaos. So they all have the same dimension. Okay, so let's go back to the original question. So I need to construct an irreducible representation for you. And well, how do I get a, say, complex vector space from an algebraic variety? Like one way would be to just take a cohomology with complex coefficients. Okay, so this is something that you can do here. And then the result, so let me say, so the theorem, so this goes back to Springer, so that's quite old. It was all proved in the 70s, basically. So the first thing is, so if I consider this complex vector space given by the cohomology, so the first statement is that you can actually construct an action of the symmetric group on the whole cohomology. And this is actually, I should mention that this is actually a quite difficult result. So the symmetric group does not act on the variety, and you have to construct it using some sophisticated machinery of algebraic geometry in general. So it's not like you just define an action on the symmetric group here, and then you get it induced on the cohomology. It's very different in general. Okay, so in particular, maybe that's one of the reasons why we really don't understand the varieties so well, because there's not a group really acting on the space itself. So this is actually quite interesting, more interesting than you might think at first. But now the point is, if I look at the top non-vanishing cohomology, So what happens then is that this is actually going to be an irreducible S lambda, so one of my Specht modules here. And, well, which one is it going to be? Well, if I pick my x here to be of the Jordan type, well, j of x, let's say, and this is precisely the partition here which I choose for my Specht module, well, this gives me exactly the representation that I construct. Okay, so in this sense, it's compatible with this picture using the partitions. Okay, so so these are basically now my two things. So this is probably what everybody likes. This is what maybe not so many people know and like yet. But so my goal is now to convince you that these things have a lot in common. So what I want to do now basically is build a bridge here. And this bridge I'm going to call Schrödinger duality. Because this is the way I can connect the two sides somehow, one possible way. Okay, so, well, before I can explain this, let me come back to this here, because I now want to recall some of the representation theory that is related to this. So, theorem, I don't know like who this is due, but it's probably some old folklore theorem which you all know. So what you can do is you can take this Temple-Lieb category and you can actually get an equivalence of monoidal categories from this category to something which I'm going to denote by fund UQSL2. So this is just a full subcategory of all finite dimensional UQSL2 representations, which are with objects given by tensor product of the natural two-dimensional representation. Okay, so this is quite easy. So I'm going to take an n, which corresponds to these n points. So now I'm just going to send it to V. So remember, so V is going to be my two-dimensional standard representation, and I'm going to send it to n copies of this, or a tensor product of n copies of this. And then there's also morphism. I'm not going to say much because you don't have to say much. Basically, this category is generated by cups and caps only. So you can build all these complicated diagrams by just stacking and, well, putting side-by-side diagrams of these elementary form. And then in this case, I want to get a map like, I want to associate a map like this. In this case, I want to associate a map like this, of course. And so this is basically just given by including the trivial representation inside this tensor product. So if you decompose this using the Clebsch-Gordon formula, you'll see an irreducible one-dimensional representation, and you just do the inclusion here, the projection. So nothing fancy, and you all know this. Yes, but sort of the point is now that I have SL2 in the picture. And this is what I want in order to go back to the bridge. So, yes. So maybe I'll put this. So Schrödinger duality. So what kind of Schrödinger duality do I want? Well, in general, I want to have a tensor product consisting of n copies of this natural representation, and I want the symmetric group to act here, and I want SL2 to act here. And then the statement of Schrödinger duality basically says that first of all, these action commute, and they generate each other's centralizer. But I'm going to come back to this now. Okay, so now the goal is to learn something from the left, or learn something about the left side from the right side and vice versa. So I think the first thing that I want to do is use this kind of stuff, or this kind of combinatorics, to learn something about this side. So basically I want to move over this way by starting here. And so let me do the following. So let me consider V tensor 2n. And so then I have an action of the symmetric group S2n here, given by permuting these factors. And here I have my action of SL2. And what I want to do is I want to consider the SL2 invariants inside this tensor product. So everything where SL2 acts by killing everything, okay? So here are my invariants. And basically this whole Schrödinger duality machinery, it gives you an explicit decomposition of this thing as a bimodule. Okay, so if you know this theory, so I'm not going to say much about it, but if you know this theory, you can check that this is actually the Specht module corresponding to this partition, where you have 2 rows of n boxes. Okay, so this comes from, say, so I'm not going to go into detail here, but this comes from Schrödinger duality. Okay, so now let's look at this board, at the theorem. So I know that this thing I can realize as, say, the top degree of some Springer fiber, where X has Jordan type, well, n comma n, okay? So I pick some nilpotent operator which has 2 Jordan blocks, and each one has size n, okay? So maybe, so this looks like this. So I pick such an X here and consider the corresponding Springer fiber. And then I know, since this is equidimensional, so we have all these irreducible components, they're equidimensional, this one has a basis labeled by irreducible components. This follows from algebraic geometry. So I might not know much about these irreducible components, but at least I know that they give you a basis of the top degree. So, okay, so let's move to this side. So what we also know is that these invariants, they are basically just hom TL. So now I'm actually specializing Q to 1 in this scenario. So I'm looking at homs from C to, maybe I'm going to put one step in between. So I'm going to look at SL2 homomorphisms from the trivial representation to this n-fold tensor product of V. So that's the same as taking invariants, right? Because it's a trivial representation. And then, so by this theorem here, no, where is it? This one, I can now translate this into diagrams, okay? So now I'm going to go to TLQ. And yes, so should I say, so this is just this, and this is just, if you look at this, what this is. So this is just the C-span of, this is the C-span of all what I'm going to call cup diagrams. So now I'm looking at diagrams from nothing to 2 endpoints, okay? Built from these pictures. So I'm going to get cup diagrams on 2 n vertices. With, say, n cups. Okay, so this is what I get from this picture. And since I'm going to need this, so the set of all cup diagrams and 2 n vertices with n cups, so I'm going to call this Bn for future reference. And so maybe I'm going to do an example. So for these cup diagrams, so if n equals 2, so I'm going to have 4 vertices on top. And well, what I have to do is construct a cup diagram like this, or like a basis element inside this space. And one possibility would be this, and the other possibility would be just this. Okay? So everyone agrees that this is everything? It must be crossingless, right? So these are matchings of these points. Okay, so that's just an example of this. Okay, so now the first thing is, obviously, I have a basis here, given by these cup diagrams, and I have a basis here given by irreducible components. So now the question is, do these cup diagrams tell me something about the actual geometric structure of these components? So that's now the hope. And it turns out that this is true. So this is now the theorem. So I should probably mention a couple of names. So this is a conjecture by Govanov. So the proof uses machinery developed by Curtis and Chemnitzer. And so the actual proof is then due to Verli and independently Russell Timotsko. Okay, so what's the theorem? So let me take A, so some diagram in Bn. So what I'm going to do is I'm going to associate to this a topological space, which I'm going to call SA. And so this is defined, so this is going to live inside a 2n-fold product of the two-sphere with itself, okay? So what is it? So it should depend on the cup diagram that I choose. So first of all, I have all these tuples, right, of elements inside my sphere. And now the cup diagram gives me certain relations on the coordinates. So what I'm going to say is, well, xi is supposed to be minus xj if I and j are connected by a cup, okay? And the minus means I'm going to take the antipode. Okay, so this is this construction, and maybe I should do an example. So let's put an example down here to see what's really going on. So let's go back to this one, n equals 2. So n equals 2, so I have these two cup diagrams. So I have to define, or I have to define for you this submanifold of S2 to the 4th power. And what this is given is basically by x, x, y, y, and I can choose x and y independently inside a sphere. Sorry, with a minus sign. Okay, so this is what happens here. Because I have the cup connecting the first and the second and the third and the fourth. So I identify these coordinates, and I'm left with two choices inside the sphere. So then, for completeness, let me also do the other one, but then you will also see what's going on here. So in this case, I identify these coordinates antipodally and these ones antipodally, and I'm left with a choice of, x and y inside S2. So this is what this looks like. Okay, but now the theorem is, so the B n, n, which is precisely this Springer fiber corresponding to this x, so this is now homeomorphic. So isomorphic in the category of topological spaces to the union of all these SA. So you can think of this as a subspace inside S2n, where you take the union over all these different cup diagrams. Okay, so that's the first result. So in fact, you can use these cup diagrams coming from the side of low-dimensional topology, let's say, to learn something about Springer theory or the topology of these components. So I also want to quickly say something, what happens if you go back. But in order for this, I need to tell you one more theorem, or one more part. So part B is about intersections. So I want to understand how these things glue. So what happens if I intersect two irreducible components, or like these topological spaces corresponding to the irreducible components? Well, then this will always be homeomorphic to a certain product of spheres. And how many? Well, it's exactly the number of circles in a diagram which I'm going to call A bar B. So what's A bar B? So A bar means I'm going to mirror the diagram. So let's say I take this diagram and I mirror it in the horizontal line containing all the vertices. Okay, so what I'm going to get is precisely something like this. So if, so let me call this one A, sorry. So this one is A, so this one is B, then this one's going to be A bar, okay, this one's going to be B, and this diagram I'm going to denote by A bar B, and so then the intersection is supposed to be given by this product, well, by a product of spheres where you basically have to count the number of circles in order to, well, know the number of factors here. Okay, so let's do this in this example, because you can all do it explicitly, so that's somehow the point of this. So if I look at this intersection, so I want to understand this intersection. So then, okay, let me choose an x here. So then I know that this one must be minus x, right? Because any element here is in particular contained in here. But now I also know that this one must be the antipode of this one. So I'm going to get an x here, and then I'm going to go back to this, and I'm going to get minus x. So you see that you have one circle, and you're also only left with one choice of x. Right? So this is homeomorphic to 1, 2 sphere. Any questions about this? I mean, you somehow have to get used to this a little bit, but it's, the nice thing is very explicit and very simple. Okay, so let's go back. Let's go to this side and look at these intersections. Okay, so now I'm going to take the cohomology of these intersections, and I'm going to take the sum over all pairs of these cup diagrams. And yes, so let me say, so this can be equipped with the structure of a convolution algebra. So this is not only a vector space, it also is a graded vector space. So it's actually, you get a graded, associative graded algebra. Here can be equipped with the structure of a convolution algebra. So this is due to Schroppel and Webster. And so this turns out to be isomorphic to Hn, which is Kovanov's arc algebra. So this is again something that most of you know very well, and maybe this side not so much, but now you can make this connection. Okay? So you can construct Kovanov's arc algebra, which categorifies this picture just using these Springer fibers. So maybe just for completeness. So what you can do, let me go back to this picture. So here, using this theorem, I can just think of this as, well, so this FD is just a map from V tensor N to V tensor M. And then I can look at, say, something, oh no, well, first of all, I'm going to restrict this to, yeah, so I should say, so now let me, only for this small part here, I'm going to restrict myself to even tangles. So Kovanov calls this even tangles. So you have actually an even number of endpoints here, an even number of endpoints here. So then I can look at the SL2 invariants inside this space, okay? So the reason for the evenness here is that I don't want this to be 0. Just a technical thing. So yes, so then the FD restricts to a linear map here, and this is categorified by Kovanov homology, as you know. So what you can do is you can look at these homotopy categories of, well, complexes of graded projective HN modules. And you have a functor here given by tensoring with a certain complex of bimodules, which I'm going to call KD. So that's a Kouranos complex. And if you take the Grothendieck group, of course, you recover all of this. Okay, so this is where you can basically construct this using, or just coming from the Springer fiber side, using this. And maybe one more thing, just for completeness, but I'm not going to say much about this. So in general, this algebra is very interesting. So it's a cellular algebra, and yeah, and it also, well, it's quasi-hereditary. Well, not quite. So you have to extend it slightly. So this one is a little bit of a lie. But so if you make this algebra a little bit larger, then you can connect it to things like parabolic category O for GL2N. You can connect it to, well, of course, Kouranos homology. So this is what I illustrated above. You can also connect it to finite dimensional representations of Lie superalgebras. Well, which one? The general linear Lie superalgebra. And yeah, one last thing maybe. So if you like diagram algebras, you can look at the non-semi-simple representation theory. So non-semi-simple means interesting, of the Wald-Brouwer algebra. And you can describe, so all of these categories using modules over slight modifications of this algebra, let's say, okay? So if you're interested in some of these things, this is also related to this. So if you want to know more, maybe we can talk about this. Okay, so this is the classical picture. So what I want to do now, in the rest of this talk, is go back to this side and actually change the Weil group, okay? Because now you can ask, okay, so now I have this picture with the left and the right side, and now in the Springer theory side, I could just change the Weil group. And what happens sort of on the other side, or something like this? Or, well, can we learn something from here using certain combinatorics, which is related to certain knot theory or knot invariants? And what I want to do is discuss this today in one example where you take a Weil group of type C. Okay, so now I'm going to look at finite dimensional irreducible representation. So let me change this slightly. So I want to look at finite dimensional irreducible representation of a Weil group of type Cn, let's say. So then it's a classical result that these are labeled by bipartitions of n. So you have, what this means is you have pairs of partitions, lambda mu, and if you think in terms of these partitions as this being a Young diagram and this being a Young diagram, then the total number of boxes is supposed to be n, okay? So then you also get, I don't know, let me call this V lambda mu, some irreducible module, just to fix notations. And the big question is, what do I put here? First of all, in order to get the picture right, just on the right side. And well, there's an obvious choice. So you can basically just replace GLM, in this case by a symplectic group, and you have the corresponding Springer theory. But there's a slight problem, because if you move away from type A, and you look at nilpotent orbits in Lie, say in classical Lie algebras outside of type A, then you don't really get a bijection here, okay? So this is a slight problem. But there's something that you can do, which was developed by Kato. So this is what I want to explain now. So what I want to do is I want to stick to GL2N, let's say, and I want to act on here by the symplectic group. Okay, so you, again by conjugation. Of course, you have GL2N acting here, and you restrict it to SP2N, and then this thing as a module decomposes as one copy of the symplectic Lie algebra plus some other sum, which I'm not going to describe explicitly. But what you can do now is you can define something called the exotic nilpotent cone. So this is what I'm going to call n sub x for exotic nilpotent cone. And what this means now is I take the old n, so that's my nilpotent cone inside GL2n. Now I intersect this with this S, so the complement of the symplectic group. And now I also put in an additional 2n-dimensional vector space as a factor here. Okay, and this is my exotic nilpotent cone, and it turns out that you get an action of the symplectic group on here. So that's basically just matrix vector multiplication. Here you still have conjugation. Okay, so now the same question. What are the orbits under this action? And in this case, it turns out that they are, in fact, in one-to-one correspondence with bipartitions, exotic nilpotent orbits. So now let me modify this. So now an orbit actually depends on a vector here and a nilpotent element. So let me label this by E, comma x, where E is a vector here and x is a matrix in here, let's say. And then there's something called the exotic Jordan type, which I'm not going to explain because it's more complicated. So there's some way to compute this explicitly. So this has been studied explicitly, this bijection, by Pramod Shah and Anthony Henderson. But it's too complicated to explain in the talks. It's not as easy as just taking a matrix, bringing it into Jordan normal from reading off some partition. But there's an explicit way to do that. And then you can actually do this. You start with an orbit here. You now go to the exotic Springer fiber, which I'm going to explain to you in a moment. So exotic Springer fiber, which now depends on E and X. And you take cohomology. Okay, and then the result is you also get an action here on the cohomology, but now actually of the Weyl group of type Cn. And yeah, so everything generalizes pretty nicely. So let me just see that I don't screw this up. So now I have lambda mu here. And so now I take this exotic Jordan type. Of E comma x. And this is supposed to be the bipartition lambda mu. Yeah, so if you take a pair E comma x, which under this bijection goes to J sub x of E comma x, and this is this partition, then you get precisely the irreducible corresponding to this partition. Okay, so let me quickly explain what to put here, how to modify this. So now I still have my flags. So they're going to be in c to the 2n. This is now what's flying around here. But I'm only looking at vector spaces up to half of the dimension. And one of the reasons is because I require these things, or let me say I'm going to require the Fn to be Lagrangian with respect to a symplectic form, which describes this setup. So this is going to be a Lagrangian subset. So then I still have my x, so my old Springer fiber condition coming from the x. But now notice that there's an additional e. Okay, so what am I going to do with it? So the e is supposed to be contained in the Lagrangian subspace here. Okay, so that's what happens. That is exactly what happens. And this is the exotic Springer fiber. And again, it's in general not smooth, and you have all these different irreducible components. Okay? So this is now the new setup. And the point is that I, again, have this one-to-one correspondence now. Okay, so now I want to understand these varieties, let's say. Yes, and So remember, in this case, I focused on the 2-row case with 2 blocks of equal size, and I'm going to do something similar here. And it's actually quite hopeless to do this in general. So this is just a side remark. But you can do it for some special cases which are of interest for low-dimensional topology, like this one. But extending this stuff to, let's say, 3 or more Jordan blocks is kind of impossible. Okay, so now the goal, so I'm hoping to finish this now during this hour, is, so I want to understand this BEX, so this exotic Springer fiber here, in the case of certain special partitions, or bipartitions in this case. So I'm considering pairs E, X inside here, such that the corresponding orbit corresponds to a bipartition which consists of 2 rows. So this looks combinatorially very trivial, but the geometry is relatively rich, but still manageable, let's say. So what I want is K boxes here, let's say, and N minus K boxes here. Okay, so I'm considering only certain bipartitions here. Okay, so now the first question, so this is kind of like a motivation. So what kind of combinatorics should I expect? Because actually I don't really know what's going on right now, so I have to think a little bit. So what kind of combinatorics should I expect, which sort of replaces the cup diagram combinatorics on this side? Okay, so in Carter's original work, so maybe I should say these exotic, I haven't really mentioned this. This is, oh, sorry. So this is actually bad. So now this theorem is actually a theorem due to Carter, okay, for these exotic Springer fibers. So in his original work, he wanted to prove the Deligne-Langlands conjecture for affine Hecke algebras of type C with unequal parameters. So this sounds very scary, and I'm not going to spend much time on this. So let me just give some motivation here. So what you're considering is certain generalized Springer fibers of this, where you additionally add a semi-simple element, let's say. Semi-simple element in your group. And there must be some sort of compatibility between the X and the S, which I'm also not going to explain. So the point of this is, you can take now equivariant K-theory of this thing with respect to some group G. So what's the group G? So let's consider this affine Dynkin diagram for type C. So I have 1, 2, 3, say n, n minus 1, n minus 2. So these are this is my affine, my Dynkin diagram for affine type C. So the G here, this is now given by the symplectic group, sp2n. And then I basically have a choice. So for the Hecke algebra, so you have an affine Hecke algebra of type C corresponding to this setup. And now you have the choice of 3 different parameters, okay? So one choice for this guy, one choice for this guy, and in the middle you have another choice for all generators of the Hecke algebra corresponding to these nodes, okay? So you have in general 3 different parameters. So I'm going to call this mode because you allow different parameters. And then for each of these different parameters you get a C star here, and that's just a group. So don't worry about this too much. This is really just the big picture. So the point is, so what Carter does using certain convolution construction is that he actually uses the K-theory or the equivariant K-theory of these kinds of Springer fibers to construct irreducible representations or standard modules and then irreducible representations of this affine Hecke algebra. And the whole point of this is, what I want you to get from this is that this affine Hecke algebra has an interesting quotient, and that's called a 2-boundary Temperley-Lieb algebra. Okay? So don't worry if this doesn't say or isn't really meaningful to you. The point is just there are exotic Springer fibers here, and they're somehow related to something called two-boundary temporally leap, because this is a quotient of this, and the Affan-Springer fibers appear when you construct these representations. So what is this? So this is an associative algebra over, let's say, C, and now you have three different parameters, delta, delta 1, delta 2, with generators. So E0. So this is now, they look kind of like this. Or maybe I'm going to do the EI first. Okay, so now this I is going to be between 1 and n minus 1. And then what it is exactly the old generator, which you are very well familiar from the ordinary temporally leap. But now for the E0 corresponding to this vertex and the En corresponding to this vertex, you get something slightly different, which looks like this. Yeah, and the same for En. So maybe I should draw this in a different color, because this is not a strand here. This is really just the boundary of the diagrams. If you think of this in terms of a box, this is kind of what it looks like. So these are connected to the frame in which the picture lives, okay? So that's just what I wanted to say. And then you can do, you have certain relations. So I'm not going to write them down. Yeah, I have 10 minutes, yeah. So I'm not going to write them down. So I'm just going to give you some feeling for what's going on with the new generators. So you have certain relations. So let me just draw this one for you. So let's put this one on top of itself. So I have this. So I'm going to put this on top of itself, which means I'm going to multiply them. So now, if you did this with this diagram, of course, you would remove the circle at the cost of multiplying by Q plus Q inverse, or in this case, say delta. And in this case, you multiply this by, so you get E0 times delta. So you remove, what this means in pictures is you remove this kind of thing, and you think of it as a circle. You just don't see the rest of it somehow. So what this is just this times, say, delta 1. Okay, so the delta here corresponds to the old circles. The delta 1 corresponds to, say, the half circles on the left, and the delta 2 corresponds to the half circles on the right. Okay, so say delta 1. So this is somehow the kinds of relations that you get. So again, so this is not the whole point, because I want to come back to this geometry. But you should somehow understand these combinatorics, okay? So you additionally, if you compare this to the old temporally leap, you have cups and caps, and you have additionally these half cups. So that's roughly speaking the story, okay? Yes, so yeah, any questions about this? Yeah, so here I'm going to put the new theorem now. Okay, so I'm going to spend 5 minutes on just explaining the combinatorics in a little bit more detail. Then I can state the result. So I'm going to look at this box. Okay, say you have a box like this, and you have n vertices, or you have a rectangle. It's not really a box. So you have a rectangle with n vertices fixed on top. Okay, so then what you can do is you allow these vertices to be connected by a cup such that the whole thing is crossingless. But now, additionally, in contrast to these cup diagrams, which appeared here in the old story, you now additionally allow these half cups. Okay, so something like this is allowed, or something like this. Okay, so that's the only difference now. So you have...
You cannot say or. Only one.
yeah, you can have this. You can put something like this. Okay, it only needs to be crossingless. So that's what it is. So these are the kinds of combinatorics. So now I want to describe the Springer fibers kind of like I did here, using these diagrammatics. And in order to do this, I have to single out something like this Bn, where I really look at certain cup diagrams, so like a certain kind, which corresponds somehow to the partition that I choose. So in this case, so as I said, I'm interested in Springer fibers, E, X, where the E, X is in an orbit which is labeled by this bipartition with 2 rows, okay? So now I'm going to say, I'm going to consider a certain subset of these diagrams, which I'm going to label by this partition on the top board, which I chose from the beginning. Okay, so think of this as this bipartition. So K, N minus K. Okay, so what is this? So this is now all these cup diagrams. So I should say two boundary cup diagrams on n vertices such that, so the number of cups plus the number of right half cups. So a cup is just what it was before, something like this. A half cup is something like this. And this one I'm going to call a left half cup, and this one I'm going to call a right half cup. So what you do here is you count the number of cups and the number of right half cups. And if such a cup diagram is inside this set, I want this sum by definition to be n minus k. That's just a definition now. But if you do this, so maybe I do an example because I think it's important when you do these kind of combinatorics. So let's do n equals 4. Okay, so n equals 4. And now I additionally have to fix a bipartition like this. So let me just choose, which one did I choose here? So let me choose this one. So that's now my bipartition. So I have 3 boxes here and 1 box here. So now I can consider this set B 3, 1 here. So these are all diagrams of this form where the number of cups plus the number of right half cups is 1. Right? K, n minus k. So how many are there? So if I have a cup, so where can I put it? So I can only have 1 cup, and the rest must be left half cups, right? So what I could do is I can put a cup here and then do this. I could put it in the middle, or I could put it completely to the right. Or, so this is all combinations where I have a cup. So if I have 1 right half cup, since everything must be crossingless, I really can only put it here. And then connect the rest with left half cups. So this is the whole set, B3, 1. Okay, so hopefully this helps somehow. Yes, so now I want to describe the theorem, which sort of describes the topology. So this is joined with Neil Saunders. So maybe before I say that, so let's consider our nice sphere. And so this is S2 embedded in R3. And I'm going to fix P, say the north pole of this. So I'm going to do this because this will appear in the theorem. So what we're going to do is we just mimic the thing that we knew from the type A theorem before. So I'm going to take a cup diagram. This time it looks like this. And I associate to this some SA. So this, again, this will live in this case inside S2 to the nth power. So there's a sphere basically for each of these vertices. And what is it? Well, it's going to be all n tuples of elements inside here, such that you have the following conditions. So xi is going to be equal to x minus j if there is a cup. So that's just as in type A. So then what am I going to do with the left and the right half cups? So for the left half cups, I'm going to say this is equal to P. So suppose vertex I is connected to the left vertical edge, then I'm going to set this equal to P. And there's no relation for the right half cup. So they always correspond to full spheres, no relations. Okay, so now the theorem is that there exists a homeomorphism from B, that's how I'm going to say it. B, yeah, so let me say B n minus k. So the Springer fiber corresponding to this orbit, okay? So above k n minus k. So this is homeomorphic again to this union. Where you take all cup diagrams inside this B. Yes, so this at least finishes like this direction. So let me say maybe 2 or 3 sentences. So what you can do now is, of course, you can also, again, take pairwise intersections of these things and construct an algebra like this. Okay, so this is basically work in progress. And it seems like this algebra is, again, very nice. It's, in this exotic case, it's also cellular, and it describes some highest weight category, which I personally haven't really seen before. So there are certain questions like what can I relate it to? And as far as the low-dimensional topology is concerned, so let me just maybe say one more thing about this, because this is probably the main interest for most of you. Yeah, so let me go back to this. So this thing here itself, so this is just a quotient of the two-pole braid group. So what you do here is basically you go back to your ordinary tangles. But you additionally have 2 poles here. So for the braid group, so this 2-pole braid group, it has the usual generators like this. But then you also have 2 poles. Let's say here's one, here's one. So these are the usual generators, and yeah. So you have, say, Bi for I between 1 and n minus 1, and this is B0 and Bn. Okay, so this is sort of the 2-pole braid group. So what I would expect is that this algebra will, at the end, have something to do with tangle invariance in this picture. And if you take the quotient of this, if you go all the way from here to here, then you see that these kinds of pictures correspond to, yeah, the generators if you go to Temple-Lilly. But yeah, I should stop. Yeah.
In type C, the Brauer algebra could appear, or the BMV algebra, which is, can you see this here?
So Daniel is shaking his head. I don't know. Yeah, I don't know, but so since you're shaking...
What the survive here we...
Yeah, so probably not, I don't know.
Small question. Do you know what B0 square is?
Yes, so it's basically something that you have, so you cannot simplify. So if you put it on, if you put this here, this is a new element.
It's a new element?
It's
B0 plus something as it is?
It's a fixed strand.
Yeah, it's a fixed strand, so this is a new element, yeah.
You are raising this with 2 points.
Yeah, exactly, yeah. Exactly. So what I would think about this is you take some disk and you remove 2 points. And then you take this cross an interval. So here's a hole in your space, and then you look at tangles inside here.